general relativity step by step. Last time I showed that if we were going to consider physics from the perspective of two different people who are moving relative to one another, we need to change the axes of time and space, and the time axis changes according to what you might expect it to change, because objects at rest move along this blue line here, but also the space axis, the axis of points that are judged to be simultaneous, also moves. So we have straight away we have a failure of simultaneity caused by the constancy of the speed of light for two observers. I just want to make a quick observation. This is going to be a very, very quick observation. That I just want to draw my black axes again. Similar arguments show here we've got the time axis moving to the right, and I want to show that if the time axis, the blue axis at least, moves the other way, let's just draw it like that. That's t bar bar perhaps. And then what happens is the other axis, the line of simultaneity, x bar bar, opens like that. And we've got this rather interesting opening out effect here. So here the axis angle gets smaller, and here the angle axis gets larger if he's moving the other way. See, here he's moving right to left, and here this person is moving left. He's in there and he's moving that way. Okay, so we've got a pair of transformations. Although I've talked about the angle of these lines, I've not really specified how time changes and how space changes along those axes. So what I want to do is to use t dash equals t over root 1 minus beta squared, which I used in the previous, or I think it was the one before last. And what I'm going to do is develop a precise set of transformations between black and blue coordinates, which is called the Lorentz transformations, Lorentz transforms. And I'm going to do that next, but I'm going to stop there because this is just a very, very short filler in. Stop.